Alright, let's have a look at the final lesson of this unit, solving systems with matrix equations. So a system of linear equations can be written as a matrix equation. And it has the form AX equals B. So we first have to put our matrices our equations from the system of equations into standard form. Very important that they are in standard form first. If they are in standard form, matrix A in our matrix equation represents the coefficients of the variables. Matrix X represents the variables themselves. This is the x or the y, or maybe the x, y, and z that we are solving for. And matrix B will be those constant values on the right-hand sides of the equations. So let's try this out with example A. We're going to write the system as a matrix equation. So first I need to change it into standard form, which means that I'm going to have to move all of my variables to the left-hand side. So my negative 5x on the right becomes a positive 5x on the left. I have a positive 2y. I have a negative, I'm just going to write it as a negative 1z, and that's going to equal negative 7. My second equation, I'm fortunate that it's already written in standard form. I'm just going to add a 1 in front of the x. You'll see why in my next step. And plus 2z equals 0. And lastly, you'll notice that I have no x's at all in the third equation, so that means I've got 0 x's. And 3y. Let's bring the negative z across where it becomes a positive 1z equals 17. And so you'll see that matrix A, which is all of my coefficients, will be 5, 2, negative 1. So it's going to end up forming a 3 by 3 matrix. 5, 2, negative 1. 1, negative 2, positive 2. And lastly, 0, 3, and 1. So that's matrix A. It is the coefficients of your x, y, and in this case we have 3 variables, so also of the z. Matrix X are our variables, and in this case we've got 3 variables, and we need to stack them vertically. And then matrix B will be the right-hand side of my standard form. That's negative 7, 0, and 17. And so if I wanted to write it in the form matrix equation AX equals B, I can now see what A, X, and B are, so I'm ready to write it into a matrix equation. I've got matrix A right here, 5, 2, negative 1, 1, negative 2, 2, 0, 3, 1, which is multiplying my matrix X, which are my 3 variables, X, Y, Z, and that will equal my right-hand side matrix B, negative 7, 0, 17. Now I'll show you why we can do this. Imagine if we tried now multiplying these matrices A and X together. What would happen? Well, we'd have, let's just make sure they're compatible first. This first matrix is a 3 by 3 matrix, and the second one here is a 3 by 1 matrix. I haven't really organized my space very well here, so just do that again, sorry. So my first matrix is a 3 by 3. My second matrix is 3 by 1. You'll notice that my inner dimensions are equal, so yes, it is possible to multiply them. And so my resulting matrix should be 3 by 1. Well, look, here it is. It's a 3 by 1 matrix, my resulting product. Furthermore, let's actually do the multiplication. So we know that in order to get the thing that is in the first row, first column, I need to multiply the first row by the first column. So I have 5 times x, there it is, plus 2 times y, look, plus negative 1 times z, there it is, and that equals negative 7, boom. And this of course happens again in the second and third equation. I'll do it quicker. 1x plus negative 2y plus 2z equals 0. That's what I have here as my second equation. And the same thing follows. 0x plus 3y plus 1z equals 17. And so now I hope you can see how to write a system as a matrix equation. Step 1 is to put it into standard form, and then step 2 is to write your coefficient matrix, your variable matrix, and their product will be equal to the right-hand side matrix. Now solving a matrix equation, which has this kind of form, ax equals b, is very much like solving a normal linear equation of the form little ax equals b. Let's just compare the two things. When we're looking at normal real numbers like ax equals b, how do we get the x by itself? Well, a lot of you might say, oh, we just divide both sides by a, and you're correct, but I want to think about it just a little bit differently. In order to get the x by itself, it would be best, one way of thinking about it anyway, is that we multiply both sides of the equation by the inverse of a. Right now, a is multiplying x, but if we multiplied both sides by the multiplicative inverse of a, which we know is the reciprocal 1 over a, well then these two elements that are being multiplied will effectively cancel and give us 1, which we call the identity. And of course, if I have to multiply the right-hand side by the inverse of a as well, so 1 over a times b. And 1 times x, the identity times anything, gives me x, and look, I've isolated x. It equals the inverse of a times b. Now let's look at matrices, and you'll see that really it's the same process going on. ax equals b. Now remember how over here some of you might have been tempted to divide both sides by a, and that would have been one way of doing it. We're not allowed to divide both sides of this equation by matrix A because matrix division does not exist. So let's try this other approach where we multiplied both sides of the equation by the inverse of A. So here we go. I'll pre-multiply. I'll talk about pre-multiplying in a minute. We'll pre-multiply both sides of the equation by A inverse, the inverse of A. Now, much like over here, we knew that the inverse of an A times the A itself cancel out to give you the identity. We know that the same thing happens here. A inverse times A will give you the identity matrix I. And we know that the identity matrix times any matrix is just equal to that matrix X. So basically the identity cancels out and disappears, just like this 1 did. And so you'll see that this identity matrix is acting like our identity element 1, and this A inverse is acting like our multiplicative inverse 1 over A. And we've ended up isolating our matrix X. It's equal to A inverse, the inverse of the coefficient matrix, times matrix B. Now, just as 1 over A, this inverse, must exist in order for us to solve this. I mean, look, what would happen if 1 over A didn't exist? That is to say, what would happen if A was equal to 0? I'm not allowed to multiply by 1 over 0. 1 over 0 is undefined. But as long as A is not equal to 0, so that 1 over A, the inverse, does exist, well then this is a valid approach to solving the equation. It's the same thing with matrices. The inverse, A inverse, must exist if we are to solve AX equals B. When does A inverse exist? Do you remember? It occurs when the determinant of matrix A is not equal to 0. Because we know that if the determinant of A is equal to 0, we know that the matrix has got no inverse. Now, when solving the matrix equation AX equals B, it is absolutely critical that we pre-multiply both sides of the equation by A inverse. That is to say that we should be calculating A inverse times B, not B times A inverse. Now, this is a big difference between real numbers and matrices. With real numbers, I suppose that we could have post-multiplied by 1 over A. I could have put the 1 over A afterwards, and it wouldn't have mattered. But with matrices, it does matter. You do not want to post-multiply by putting an A inverse here. That would be incorrect. So you want to calculate A inverse, the pre-multiplied A inverse times B, and not B times A inverse. Why? Well, simply because these two matrix products are not equal to one another because matrix multiplication is not commutative. So the order in which I multiply the matrices will change my product. So it's very important that I put the order correctly and that I have my A inverse at the beginning of each side of the matrix equation. So we had this matrix equation that was in example A. Let's actually try to solve it now. So remember that we had this matrix 5. I might have to just refer to it quickly. Where are we? 5, 2, -1. And that was multiplying x, y, z to give us -7, 0, 17. And my other rows were 1, -2, 2. And 0, 3, +1, I think. Yes, 0, 3, +1. So there's our matrix equation. We need to solve this. Now remember that the principle is that we are going to pre-multiply both sides of the equation by the inverse of matrix A, by the inverse of our coefficient matrix. So we're taking 5, 2, -1, 1, -2, 2, 0, 3, 1. We're going to take the inverse of this matrix A, and we'll pre-multiply it on the left-hand side. And we will pre-multiply it on the right-hand side. So again, we take our matrix A inverse. So whatever I do to the left, if I'm pre-multiplying by A inverse, I've got to pre-multiply the right-hand side by A inverse. And this is multiplying my matrix B, -7, 0, 17. Now what do you get when you multiply A inverse by A? You should know that we end up getting the identity matrix, because they're inverses of each other. And so we're taking the inverse of this and multiplying it by -7, 0, 17. Now what's the identity times our variable matrix x, y, z? Well, of course, that just gives us the x, y, z, doesn't it? So in order to get our solutions, I just have to do the multiplication of A inverse by B. To do this, I need to enter my matrix equation. So I'll say second matrix, and I'm going to edit a matrix called A, and I want it to be 3 by 3. Let's put in the numbers 5, 2, -1, 1, -2, 2, and 0, 3, 1. And now then I'll quit. I'll come over and I'll edit a brand new matrix called matrix B. And matrix B is going to be a 3-row by 1-column matrix. And it's going to be values -7, 0, 17. And now let's quit. And I want to take the inverse of the matrix named A. So let's call up matrix A, the matrix named A. And I'll put a -1 beside it, so I'm calling up the inverse of A. And I'll multiply it by the matrix that is named B. And I get my answer. So x, y, z is equal to -2, 4, 5. And right at this point, you might be thinking, well, okay, I can kind of get it, but why would we go through all of this when we got things like substitution and elimination? Believe me, when you get to larger systems of equations, this is going to be a much more efficient method. In fact, we don't really need to do very much work at all. Once we've written the matrix equation, we just know that our variables are going to be equal to the inverse of the coefficient matrix that we can figure out in the calculator times the right-hand side, and we're done.